Hello everyone, and welcome to another Leetcode video. Today we're looking at the problem maximize the number of target nodes after connecting trees 1. And this was question 3 in weekly contest for 26. So the question reads that there exist two undirected trees with n and m nodes respectively, and have distinct labels from the range 0 to n-1 and 0 to m-1. So we're also given the edges for those two trees that represent the relationship between those nodes. So essentially an undirected edge that says that if there exists A and B, there is an edge undirected between those, and for the second tree, there's also an edge UIVI between those two. So here's where it gets a bit confusing. Node U is target to node V if the number of edges on the path from U to V is less than or equal to an integer k. And a node is always target to itself. So essentially what we want to find here is for a node, how many other nodes fall within the range k from that node. So what we want to do is return an array of integers where the answer for each element is the maximum possible number of nodes target to node I. But the catch here is that we can actually connect two nodes from the trees. So for example, we could take node 0 from tree 1 and node 0 from tree 2 and connect them. And what we want to do is do the query on that connected tree. So for each answer, we have to find the maximum possible nodes that we can get if we were to connect two random nodes in those trees. So looking at an example, we would get the output 97988 here. And how do we get this 9, for example? So if we were to connect I0 to this 0 here, so 0 to 0, you'll see we could get to 9 other nodes within a range of 2. So we would have 0 ourselves, and then we'd have the other nodes 2, 3, 4, 5, 6, 7, 8, 9. So it can be shown that if we connect these nodes, we could get to all 9 of those nodes. But remember, we could have connected 0 with 2, 0 with 7, 0 with 3, with any of these nodes. So we have to find the maximum we can get if we just connect two random nodes, essentially. Let's look a bit closer at this example. So we're given these two trees here. So how would we actually go about solving this? So essentially what we have to do is we have to start at each node in this tree and see if we say start at 2, we can connect any node to any other node here and just see the maximum amount of nodes that we can reach in a distance of 2. So obviously we could brute force this, right? We could say start at 0. We're checking for node 0, try every node here, connect to every other node here, and just see what we get. But this is going to be kind of inefficient, so there must be a better way to do this. Well, let's think, for example, if I'm starting at 0. Well, here I know that I could kind of break this up into two parts. I know that I want to check for all the nodes that I can get in a distance of 2. So really, I can check my own tree first. So what if I say, okay, I can get to 0, I can get to 1, I can get to 2, I can get to 3, and I can get to 4, right? Okay, so this makes sense. Like we could do this in our own tree, but how does this other tree come into play? Well, I could maybe try, again, connecting all those nodes, but that's going to be too inefficient. Well, what if we handled this part separately, right? So what if, forget about this tree, what if I started here? Well, here, what we need to do is adjust our k value. So instead of k, we're going to do k minus 1. And why are we looking at k minus 1 equals 1? Why are we doing this? Well, you can imagine that, say we do connect this 0 to 0, right? This is basically one step that we've taken. We've already taken a step of 1. So really what we're simulating here is that we can look in this tree, but what we could do is say, well, I had to have taken at least one step to get here, so let me find all of the nodes that are 1 away from me, right? So I can go here, I can go here, and I can go here, and also include myself as well. So basically, what I've seen is that I have 1, 2, 3, 4. If I were to connect directly to this node, then I have one more step to go, and I can go to all these places. So usually here we have 5, see we have 4 here, and this equals the 9 that we expect in our answer starting from this first node. But Again, that doesn't answer the question of how do we actually do this optimally, right? Do we have to try and connect every single node? Well, actually, we don't, right? What we could do is before we actually try to generate our answer, we can just pre-process this tree. And why can we do this? So say, for example, we're starting at 0 like we just said. No matter what node we connect with, right? If we connect 3 to here, 1 to here, 2 to here, we're always going to be getting, at best, this case, right? We're always going to know that we can go one distance and do this. So really what we could do beforehand is for this tree here, we could do a BFS from every single position, right? So here we've seen what happens if we do 0. If we start from 1, for example, we could go here, we could go here. I think that's it. So what we're going to do is we're going to pre-process this tree. We're going to start at every node, and we're going to see how many nodes we can reach with k minus 1. Right? So then once we have this, we can store it in a hash map. So say we have for 0, we can get to 4 other nodes. For 1, we can get to 2 other nodes. Say for 2, we can get to 0, 7, 3. So here we can put 4, right? So that's what we're going to do. We're going to do a BFS from each different node and record the answer in a hash map. Then what we're going to do is once we have this information, we can do a BFS starting from here. So what I could say is, all right, let me look in my own tree and see how many I can find. So I'm going to do this here. And then once I have that, what I could say is, well, now I know that I can connect this 0 to all these different ones, but I've already done it, right? I know what the answer is going to be for every single one. So I can just look whatever the maximum value is here and just take that value out. Sorry, and this should be a 5. So really what we're doing is we're pre-processing, and we're going to record these BFS values for the second tree because we know that they are not ever going to change. And then what we can do is for each node here, we're going to find how many we can reach in our own tree, and then also the maximum that we can reach in this other tree. So what is the time complexity here? Well, to generate all these different values, this is going to be an O of m squared process because we have to start here, we have to go to every other node, then we go to 2, go to every other node, go to 3, go to every other node, right? So it's definitely not an efficient process. It's going to be O of m squared to do this. It's similar on this tree, right? We start at 0, we have to see how many nodes we can get to, then we have to go to 1, see how many nodes we can get to. So over here, it's going to be O of n squared as well. So we're just doing these separately though, so it won't be multiplication, but be addition. So what we can do is O of n squared plus m squared, which will be our final time complexity for this problem. Let's look a bit closer at the code and see exactly how this works. So the first thing I want to do here is set up a breadth first search function that I can use for both trees. So it's going to be pretty generic. What I'm going to do is just keep a count, and I'm going to start a queue, which is pretty standard for breadth first search. The only thing is here, I'm passing in this current steps. And what this represents is either if I'm in my tree n, the original tree, my current steps is going to be 0, right? Because I'm starting at that root node and not having moved at all. However, if I'm doing the other tree, the m tree, I'll know that I have to have moved at least one step, right? To connect a node from the n tree to the m tree, I have to do one step to get there. So we're going to pass in a 1 here to know that we actually have to go one less step in this case. I'm also going to have my seen node set where I'm just going to keep track of nodes that I've seen already. Because remember, this is a undirected tree, so we could potentially go back to nodes that we have seen already. Then I'll do my breadth first search. I'm just going to pop off my queue. If the steps is ever greater than our k, we know that it's out of bounds and we can't go there. Or if we've already seen the node, we continue. Then we're just going to add that node to our seen node set. We're going to increment our count by 1, and then just process all our neighbors and put them on our queue. So here's the actual logic of the question. We're going to have our n and m graphs, and we're just going to set those up based on our edges. Remember, these are undirected, so we're going both ways. So what we have here is our answer array, and this is going to be the final answer that we return, and then something called m answers. And remember, for that m tree, what we're going to do is we're going to go and pre-process every possible scenario that we can, right? So we're going to know what's the max we can get starting at node 0, at node 1, at node 2, etc., which is what we're doing here. We're going through every single key, and we're just doing a BFS, assuming that we've already moved one step. Because remember, to connect from the N tree to the M tree is going to take one step. And we're just going to record that here. Then what we're going to do is we're going to go through every node of our original N tree, right? And what we're going to do is do a BFS again, and we're just going to figure out how many nodes we can reach in our own tree. Then we know that whatever our answer is going to be what we found in our own tree plus the maximum we can get by connecting to a node in another tree. Remember, we've already figured out the answers for every node we can connect to, so we can just get the maximum from our values, and we're just going to return that. So finally, we just return our answer. So let's submit and make sure that it works. And it does work. So hopefully this is helpful and it made sense. If you liked the video, please like and subscribe, and thank you for watching.